This conference will now be recorded.
Good morning, Mananda. Today I would like to explain one more topic of the second unit, subject microprocessor, microcontrollers. So till now we have seen about the overview of microcontrollers, overview of 8051 microcontroller, features of 8051, applications of 8051, and I/O ports, memory organization along with registers. Today I would like to explain one more topic of microcontroller, that is addressing modes and instruction set of 8051. So if you understood this topic, then only we can go to the next topic of 8051 real-time control. Because here you can say that it is related to programming timer interrupts, programming external hardware interrupts, programming serial communication interrupts, programming 8051 timers and counters. So here we are seeing that programming. So this program may be hardware programming or software programming. So how can you perform that hardware programming or software programming will be explained with the help of address units and instruction set of 8051 microcontroller. So here that's why here I would like to explain some of the topics which are related here, interrelated. They are known as addressing modes, assembler directives, instruction set, and some of the example programs that we can understand how to write the programs. So these are the required field to understand the programming of 8051. So these are some of the examples of 8051. And here some of the examples of instructions I have given. Move R2 comma hash 55. Increment R2. Increment and jump on no zero R2 comma target address. And jump. Yes, jump. NO, no operation. MULAB. Right. So here we are seeing that different instructions. Movements moving the data from source operand to destination operand, same as the 8086 programming. Decrement argument, the content of R2 will be decremented by 1. Decrement and jump on no zero. Right. The R2 comma target, the R2 value will be decremented and jump to the target address. Right. So what are all these instructions that we will see, and these how these instructions are written will be explained in this presentation. Right. But here we have to remember, let's find how long it takes to execute each of the following instructions for a crystal frequency of 11.0592 megahertz. So the machine cycle of the system is 11.0.90 is 1.085 microseconds. Why? Because the time period is the reciprocal of the frequency. Megahertz means frequency of the 8051 microcontroller. So here mission cycle. So some instructions require one mission cycle, and some instructions require two mission cycle, and some instructions require four mission cycles. So how much time? So time is nothing but one mission cycle time into right the number of mission cycles. So suppose if you want to execute move R2 comma hash 55, it requires one mission cycle, and for one mission cycle the time is 1 into 1.085 microseconds. So it is 1.08. Suppose if you want to execute multiplication or division operations, then it requires four mission cycles. So the total time it takes is 4.34 microseconds. That's why when we are executing a simple operations or the operation like multiplication and division, it takes some different times to execute the output. So that you can observe while executing the programs. Right. In 8051, we are having 6 types of addressing modes. First, we will see what is an addressing mode. 3 types of instruction set, that is 1-byte instruction, 2-byte instruction, and 3-byte instruction that I will show you here. Right. So this is instruction format. Usually we have the instruction format like label, opcode, operand, and comments. Right. Label is nothing but here. Suppose you want to write the repeat instructions, then that repeat instructions will be executed with the help of a label. And opcode is nothing but operational code. In 8051, we are having 251 operations, opcodes. So instructions also 251 instructions are there. Right, operands. So this operand is two types, destination operand and source operand, and these two are separated by a comma. Right. The source operand and destination operand before execution, they are acting as inputs, but after operations, right, this destination operand acting as an output operand. Right, that's what it's called as destination operand. And these instructions are 1 byte, 2 byte, and 3 byte instructions. In the 1 byte instruction, 2 byte instruction, first byte is opcode and second byte is operand. And 3 byte instruction, first byte is opcode and next to second and third bytes are operates that we will see. For example, here I am given one instruction based on L call. L call stands for long call. This call instructions are executed helps to execute interrupt instructions, and in this this is the 3 byte instruction. 3 byte means 1 byte equal to 8 bits, so 3 into 8 equal to 24 bits, or 24 bits represented with the help of 0 to 23. So here first byte means this is the first byte, even though we are representing with the last one, but we are moving from right side to left side, so that's what is called as the first byte. So this first byte is this first byte is here instruction opcode. What is opcode? L call, right? And next to 2 bytes is target address. Why 2 byte target address? Because in 8051 we are having 16 address lines. So this L call can move from any place to any place, that is from internal memory to external memory or external memory to internal memory. So the target address may be up to 16 bits or 2 bytes of instruction. So complete it is called as 3 byte instruction. This is an example of 3 byte instruction. And here we are having one more LJMP. LJMP is also 3 byte instruction that we will see later here. So now here, how to execute this mission cycle in terms of 1.0. Here you can understand that. So in 8051 block diagram, if you see that CPU is receiving the from the clock generator, and clock generator is input from the oscillator. This oscillator may generate 12 clock pulses, right? 12 clock pulses, and these 12 clock pulses are referred as state 1 to state 6, and the state 1 to state 6 are 12 clock pulses is termed as the one mission cycle. Why we are taking these 12 clock pulses is nothing but because here 8051 basically operating at 11.0.92 megahertz or approximately 12 megahertz. Why 11.0.92 megahertz? To meet the required part rates, they are taking odd number of 11.0.92 megahertz. But it may be operated at 12 megahertz also. Right. So this 12 megahertz is divided by 12. So then it gives the 1 megahertz of the clock frequency. Okay. So that's why they are taking like that. And see here, the time period for one clock cycle is equal to 1 by f. So it is 1 by 12 microseconds. So for one state and two clock cycles, this is called state 1. S1 is called state 1. It is taking two clock pulses. So here 2 into 1 by 12 equals 1 by 6 microseconds. So one mission cycle equals 6 states. That's why it's taking 6 states. Okay, so time period of one mission cycle equals 6 into 1 by 6 is equal to 1 microsecond of time period. So that's why to execute at least basic 1 byte instruction requires 1 microsecond of time if it is 1 megahertz. Right. So what is addressing mode? Addressing mode is nothing but the way in which the data sources or destination addresses are specified in the instruction that moves that data determines the addressing mode. The ways by which these addresses are specified are called as addressing modes. Right? To reach my home also, if you say that please come to my home, there are different ways of addresses to reach my home. Same as your home also. Right? You always we say that the best way is the shortest way or shortest address. But here we can reach our home different ways and different addresses. Like that here also, different ways are there to write different instructions. So they are immediate addressing mode, register addressing mode, direct addressing mode, register indirect addressing mode, indexed addressing mode, and implied addressing mode. These are the 6 different addressing modes to write the different types of instructions. So before going to the types of instructions, first we should understand in different address modes. What is address mode? The way in which the data sources are destination addresses are specified in the instruction that moves the data determines the addressing mode. Right. So this is what we call the address mode definition and types of address modes. First, we will say the immediate address mode. So this immediate address mode is also part of in 8086. So in this immediate address mode, the data is provided in the instruction itself as an immediate number. So that's why it is called as immediate addressing mode. The data is provided immediately after the opcode. That's why it is called as immediate addressing mode. So these are some of the examples of immediate addressing mode. So for example, so move a comma hash 0af, move r3 comma hash 45h, move dptr comma hash fe00h. Right. So here we are having a 0af. Here also 0 is missing. Right. If the hexadecimal numbers are from A to F, then we have to write 0 before this A to F. Here also 0 is missing, right? Because A to F, otherwise it will be treated as A to F as a characters. But here AH to FH are the hexadecimal numbers. So that's why here we have to write 0 before this number, right? H stands for hexadecimal. 45H is 4 and 5 are the two decimal numbers. So here hash is indicated. That's why it is called as the 45H. In these instructions, the hash symbol is used for immediate data. Right. So in the immediate address mode, the hash symbol is used for immediate address mode. In the last instruction, there is a DPTR. So the DPTR stands for data pointer. Using this, it points the external data memory location. So in the first instruction, the immediate data is A of H, but 10 is added at the beginning. So when the data is starting with A to F, the data should be preceded by 0 here. Okay, DPTR is a 16-bit register. So that's why here we are taking 16-bit. How 16-bit? FE00H. FE00H means 16-bit address. 16-bit value because 1H is equal to 4 bits. Right. Register addressing mode. In the register addressing mode, the source or destination data should be present in a register R0 to R7. These are some of the examples of register addressing mode. Right. Means here destination operand and source operand both are register values. We know that A is the accumulated register and R5 is the fifth register. So here, if you move the content of the R5 to A register, so in the register address mode, we have to write move A comma R5. Both are registers. Move A comma R0. Right, these are also registers. But move R5 comma R7, move R0 comma R2 is not possible because it won't allow to move the content of register to register in 8051. As in 8086 also we know that memory to memory transfer is not possible. Right. Register address mode. These are also some of the register address mode. Suppose if you want to write R7 to R5, then you can write this 07H to R5 and R7 to 05H. Then what is the name of this instruction? Right. So see here, we are having these instructions. First 002 7FH is called as 128 lower address memory locations of RAM memory. And here you can address the data, address the register values as 002 7F or R02 R7, 202 2F, and 3027F, like that also we can address. That's why here we are having direct and indirect. These are called as direct and these are called as indirect addressing. So here 802FF and P02B. These are also direct addressing. And in the indirect addressing, we can write as 802FF. Instead of P0, you can write 80. Instead of P1, we can write 90. That's what is called as indirect addressing mode. So here, how to write this direct addressing, indirect addressing, that we will see. Suppose in direct addressing, if you write move 80H comma R6 means the content of R6 is moved into 80H. What is 80H? 80H is an address location of port 0. Here you can see that P0 address location is 80H in SFR. And SFR means special function registers. So what is special function here? 80H is the address location to execute the port 0 address. So that's why here we have write. So move R2 comma 45H. So what is 45H? 30 to 7F. 45H is the in between 30 to 7FH. So here we are taking the address, direct address. Whatever the content is stored in the memory location 45H will be copied into R2H. Move R0 comma 05H. So what is 05H? 05H is the indirect direct address value of 05 R5 is copied into R0. Which is the indirect address mode. In this addressing mode, we use @ symbol for indirect address mode. And in this mode, we have to remember some point. The source and destination operand is given to the register. By using register indirect address mode, the internal or external addresses can be accessed. Both can be accessed. The R0 and R1 are used for 8-bit addresses. Only two registers will be used. And DPTR used for 16-bit address, and no other registers can be used for addressing purposes. Only these three addresses we use: R0, R1 for 8-bit and DPTR for 16-bit, and we use symbol. If you use symbol, it is called indirect. If you don't use means it is direct. That's how you will see that. Suppose you see, I want to contain the R0, this location of R0 to E5. So that's why what I'm writing, move R0 comma hash 40. So R0 E value is equal to 40. Now if I write move 0 E5H comma at the rate of R0 means the 40th memory location is indirectly specified with the help of two instructions. Right. So here I want to write copy some data from 40th memory location. So that's why here we are writing move R0 comma 40. So then R0 becomes 40 H equivalent. Then that is pointed out by @, then it becomes indirect address instead of immediate value. Then whatever the content is stored in the 40th memory location, that will be copied into the E5H address. What is E5H? Here you can see that 98, B8, B0, E0, and E1, E2, E3, E4, E5 is there between B0 to F0. So whatever the content is stored in this E5H address location will be copied by the R0 address location. That is what we call the register indirect address mode. Right. And here we are having one more example also. Move R1 comma hash 30 and move at the rate of R1 comma 80H. This is called destination operand. This is called source operand. Port 0. 80H is the address location of port 0. That's why here port 0 content is copied into the address location of R1. R1 is called port 30 means the port 0 value is copied into 30th memory location. And indexed address mode. So here indexed address mode is done by the two instructions move x8 comma at the rate of development or move c at the rate of here and that will see move c later. First we'll see move x a comma at the rate of r1. X stands for RAM memory. C stands for ROM memory. It is program memory. So if I write move X A comma at the rate of R1 means the content of R1 memory location is moved into A register. So how can say that it is related to RAM memory because R1 is the RAM memory location. Move X at the rate of DPTR comma A. The content of accumulator is copied into the address location of DPTR. So this DPTR is a part of our SFR RAM memory locations. That's why these two are related to our next addressing registers related to RAM memory. Right. So here MOVX indicates the external data memory. Next, one more instruction. These are some of the examples of MOVX. MOVX A, comma, at the rate of RP, MOVX A, comma, at the rate of PTR, MOVX at the rate of RP, comma, A. See here, we are using only accumulator register. We are not using P register. We are not using any other registers. We are using A register as a source operand or destination operand, and we are taking as R0 or R1. Here R2 stands for either R0 or R1 registers. And one more is code memory, read only data memory. Right, so this code memory is move C A comma at the rate of A plus APTR. In this code memory instructions, we don't use R0 comma R1. We use only either accumulate register or TPTR register and program counter only. Why? Because R0 to R7 are a part of RAM memory, whereas this core memory stands for ROM memory, RVM memory. That's why here we use accumulate register, program counter register, and DPTR register. Program counter helps us to execute the address of next instruction, whereas DPTR helps us to execute 16-bit data, 16-bit addresses. So here we are having one more move C, move C A comma at the rate of A plus DPTR. Right, so that's when here copy the code byte found at the ROM address formed by adding A and the program counter. So it is copied into A register. See here, right? So here RAM memory and ROM memory is interfacing. How to call the data from RAM memory is will be explained here. So this is A register and this is R0 or R1 registers. Right. So here we use A register and R0 to R1 is RAM memory. Internal RAM and external RAM. Here you can see that move X A comma at the rate of I. Right. How much move X A comma at the rate of TPTR. Right, understand. So here these two are related to RAM memory. And here this is related to ROM memory. We use move C A comma at the rate of A plus DPTR, move C A comma at the rate of A plus PC. We don't use R0 to R7. That R0 to R1 or R0 to R7 are related to the internal RAM memory. Yes, in this way, we can call this RAM or ROM data into 8051 or 8051 to RAM or ROM. Next, some useful assembly directives. And before writing any programming 8086 or 8051, here we use some assembly directives because these programs will be run on some of the assembly programs. So these assembly directives are, for example, end directive, origin directive, equate directive, data directive, and bit directive. Right. Data is nothing but to represent data in terms of system bit data, 32-bit data, so no average data, no average here. Average is nothing but variable. Data is the type of value representing, and bit is used to assign a symbol name to a bit and bit addressable data memory locations. Equate directive used to equate a name with an address or data value that I will explain. Origin directives set the location counter address for the following instructions. Last line of the code assembly will not compile after this line. So here, for example, what is origin? Org stands for origin. Origin means initial or stating the starting of the address. Right. So the ORG directive is used to indicate the beginning of the address. The number that comes after ORG can be either in hex and decimal. If the number is not followed by H, it is decimal, and the number an assembler will convert it to hexadecimal internally. And this indicates to the assembler to the end of the source file. For example, you see here I'm explaining I want to compute z is equal to x plus y. It is an arithmetic operation of addition. Right? How should I write? I have to write this expression as x EQU 78, y EQU 79, z EQU 78. See, EQU is what is EQU? EQU is an equate directive used to equate a name with an address or data value. Right. So x is equal to 78, y is equal to 79 hertz, whereas z is equal to 78 hertz. So now ORG 0008. See here, ORG is an assembly directive. ORG is an assembly directive used to indicate the starting address as 000H. We can write any address instead of 000H, but it is a default address location, starting address location. X content move a comma x. X is source operand and A is destination operand. X content is moved into accumulator. Add a comma y. What is y? 79h. So the content of 78h and 79h will be added, and the result again stored by this A register. It is accumulator. Now I want to move this accumulated data to some other location because I want to use this accumulator for some other operation. Then what should I do? Right. So then the content of A register is moved into 7AH. So here 7AH is the address location, not the data. So now come to this instructions. So in 8051, we are having a total of 255 instructions. And the instruction set of 8051 can be divided into following instructions. We know that we need data transfer instructions, we need arithmetic instructions, logical instructions, program counter instructions, and bit manipulation instructions. To perform bit manipulation instructions, here we need bit manipulation instructions. Here program control instructions are called jump instructions. Logical instructions are also called Boolean instructions. Arithmetic instructions are nothing but addition, subtraction, variable arithmetic. And data transfer. How to transfer data using Boolean instructions that we will see, for example. Right. Data transfer instruction. This is also something I have seen that rotate and swap instructions. They are given jump and call instructions also. They are given jump and call only called as program control instructions. Rotate and swap are called as the bit manipulation instructions. And so this slide shows that it's not clear, but this slide shows that how to move the data from one memory to another memory, from accumulator to register, register to accumulator, and so on. And here these are the instructions we use in data transfer, arithmetic, logical, boolean, programming, branching instructions. In data transfer, we use move, move C, move X, push, pop, exchange, and exchange instructions. Arithmetic instructions add with the aggregate, subtract with borrow, increment, decrement, multiplication, division, DAA, data adjust operation in BCD operations, logical operations, ANL, ORL, XLRL, AND gate, OR gate, exclusive, clear, complement, rotate left with carry, rotate right with carry, and swap instructions. All are called logical instructions. Boolean instructions are nothing but clear, right? Set bit, move, JC, JNC is all called Boolean instructions or bit root instructions, and branch instructions how to jump from one location to another location. Always we could not write 3 to 4 lines of the program. Sometimes we will write 10 lines, 15 lines, 20 lines, 100 lines of the program. And we keep on writing the program instructions. Sometimes we need to go to the previous instructions, or sometimes we need to from that location to some other instructions that we use them to do this branching instructions. So here some of the data transfer instructions. So by using move instruction, we can write in different ways by using different addressing modes. If I write move a comma rn, this is called register address move. Move a comma at the rate of r, it's called immediate address move. Move a comma hash data hash, you get immediate address move. So like that, by using different address modes, you can write in different ways of new instruction. Right. And push and pop instructions are related to stack and to execute the instruction. And exchange instruction. Exchange register with accumulator means the content of Rn goes to A and A content is moved into the Rn register. Whereas in the case of move, right, if I write move A comma Rn means R0 or R1, right, that Rn or R0 value, the content of the register stored in the register is moved into A register only, but A register data will not move to Rn. Suppose if you want to perform such kind of operations, then we have to use exchange instruction. Exchange A comma Rn. So exchange register with accumulator. Exchange A comma direct. Exchange direct bind with accumulator. Exchange. And we have one more exchange A comma data Ri. Exchange lower level indirect with RAM with A means whatever the address is specified by this R0, that address will store some data. That lower byte value is copied into the lower byte of your accumulator. Move A comma ACC is an invalid instruction because both are same. A or ACC means accumulator. So move data using move, merge, move, save, cushion, popcorn, exchange instructions. Now, external data moves, we have seen all the data moves. Move x, a comma at the rate of rp, move x, a comma at the rate of p. Means in 8086 we are having only one move, but in 8051 we are having three moves. Right, move x, move, and move c. And move x for RAM data locations, RAM memory data locations, and whereas move c is for raw memory data movements or copying and transferring from memory locations to accumulator. It's called as move c. Cushion part instructions that we have seen in the stack instruction. The cushion part of course specifies the direct address of the data. The data moves between an area of internal RAM known as stack and the specified direct addresses. Suppose here you can see that that explaining. So these cushion part instructions are touch location starting from 80H to 7F or 30 to 7F addresses. And this push me to increment the SP value by 1. Pop means it incremented the SP stack pointer value by 1. So that is the cushion part instructions. आजकल means without and bar logic, exchange bar logic. A and L, A comma R N means the content of A is entered with content of R N. So why it is both are we can write A comma R N, it is 8-bit register and it is also an 8-bit register. So both 8-bit registers can be conveyed easily. So that's why we are writing A comma R N. A and L, A comma at the rate of RI. It indicates indirect address. At this address location, there will be some predefined value. That predefined value must be comes of 8-bit because accumulator is an 8-bit value register. Right. Clear A means the content of accumulator will be copied, will be completely clear to 0. Complement A means the content of A will be complemented to 0 to 1 or 3 is 1, 1 to 0. Rotate left with A means the content of accumulator is rotated to left side and rotate right and swap instruction. We will see what is swap and next side. These are all different instructions. Complement one. Arithmetic operations, so we know that functions of fraction multiplication is basic mathematical operations. So here also the instruction can be written like this: ADD A comma hash data. So here it is called as opcode, and here it is called as destination operand, and here it is called as source operand. So the content of A will be added with the content of source operand of all these things. And result again stored in A register. That you can see here description. And A is pointed out by A plus data. So A plus data means A is added. Here the content of accumulator is added with immediate data and results stored in A register. Then after these are different address modes. How many bytes of data, how many machine cycles are required here are given. So INC means incremental, DEs means decremented, incremented by 1 byte and decremented by 1 byte. See, here I am giving one example how to add the values. So clear C means C stands for carry. That if there is a multi-program segment where those 6-bit numbers, the numbers are 3C, E7H and 3B 8DH, place the sum in R7 and R6. R6 should store the lower byte. So how to add that? Move A comma hash E7H. Then add A comma 8DH. See, you know that when you're adding any 16-bit numbers, any two numbers, first 7 will be added with D, and E will be added with E, C will be added with B, and 3 will be added with 3. Like that, it will be added. And it will not add 3 with 3, 3 will be like that. So this is one number, this is x1, assume that this is x2. If you write x1 and x2, then it will be added at 7 with B. So that's why here we are taking in A, we are taking lower byte of the first value E7, and they add A comma 8D. So this 8D is the x2 lower byte, so it is added. And result will be stored in A. If there is a carry, that will be stored in the carry of the PSW register. And now here the content of A will be sent to R6 because it is part of the lower byte, right? Because we are adding two lower byte values, so we are sending it to R6, which is a lower byte. Now move A comma hash 3CH. What is 3CH? Higher byte of the x1 value and add with the carry because we are adding to 700D, which is more than F for 16. That's why carry will definitely generated. So that's why here we have that ADDC. ADDC stands for add with carry A comma hash 3BH. What is 3BH? 3BH is the higher byte of the next value. And now the result is stored in A register. So here we are sending R7 comma A means the content of A is sent to R7. So place the sum in R7 and R6. R6 should store the lower byte. See here R6 and R7 storing the result and R6 is storing the lower byte. So simple example, we can add 16-bit values also like that. Suppose I want to add two 8-bit values. How to write? Right, move A comma hash 45, move B comma hash 86, add A comma B. Suppose if I actually program should start like this, program should start ORG. But if I don't write ORG 000H means right initially or by default it will take ORG as 000H. But it requires at least one AND statement. Add A comma B. So A is hash followed by H. H stands for hexadecimal. B stands for 86H. Hexadecimal. So two hexadecimal numbers means 8-bit value. So here A and B are also 8 registers. So we are add A comma B and result again stored in A register. But I want to store this data in some other memory location. So that's why here I am writing move 20H comma A. And is the N directive. So this is multiplication and division operations. Right. For that we have to write one A comma B and two A comma B. So coefficient is stored by A register and remainder is stored by B register and coefficient and remainder is again stored into some other memory location because I don't have any hash here. If I don't use hash, that is called as direct addressing mode. So if I use certificate, it becomes indirect addressing mode. I am taking here as 44 and 45. These two are the direct address locations. So this is also presenting this just after the operation we provide DAA and it will be adjusted to equal decibel instead of hexadecimal jump operations. So jump to specific address locations are branch specified labels. So this branch, jump or branching instructions are control instructions are mainly provided based on the program size. So the program size may be 128 bytes or 2K bytes or 164 kilobytes of memory. So here, that's why here we are having anywhere to anywhere, right? 60 up to 64 kb. 64 means F, that's why here this bracket taken from here to here. It's called LGM. If jump instruction is up to 64 2 kb, 2 kilobytes of memory locations, because all the programs are not lengthy programs. There may be some medium type or medium size instructions up to some 1K or 2K and so on. So such the type of programs will use AGM. And if the instructions are 8 bits, 256 bytes of instructions, and the range may be defined as minus 128 plus 127, so then we use SJump instructions, and these SJump instructions are all using conditional based instructions. Without any condition checking also we can jump to MJump and AJump, that we will see later. And one more branch instructions are call and jump instructions. So what is difference between jump and call instructions? A jump instruction permanently changes the program counter, whereas call instruction leaves information on the stack so that the original program execution sequence can be resumed. Means the call and return instructions are used when interrupt is executing, when no main program is executing continuously. Then there is need of executing interrupt. This interrupt is called a subprogram. Then this call interrupt will call the stack and using push instruction, we keep this main program address on the stack and the subprogram will be executed. And again by using the RET instruction, the main program return address will be written into the main program execution. That is what we call the call instruction. And this call is similar to a jump, but call instruction pushes the, as by using push instruction, pushes the program counter onto the stack before branching and allows return back the main program. This I can explain with some of the examples of programs. Call instructions are two types: L call and A call. L call for long call. It has 3 byte instruction. Call any subroutine entire 64 kilobytes of memory because one is having 16 address lines, so we can have 2 for 16 and 64K. And A call means address means 2 byte instruction and call any subroutine within 2K of hardcore space. Other than this, same behavior as L code saves code ROM for devices with less than 64K ROM. Right. Suppose if any device is having 64K and less than 64K ROM, then instead of L call we can use A call. RET, return from a subroutine call pops PC from stack. Okay. These are some of the instructions of call and jump instructions. So the jump instructions are two types: unconditional jump and conditional jump. Conditional jump means this instruction type will load the program to a new address and will automatically jump to the instruction at the address. As conditional jump, this instruction type will only jump if the certain condition is true. If the condition is not satisfied, then it will not execute next instruction. Same as the similar if statement in C language. So that's why here these are the unconditional jumps in 8051. Yes jump, L jump, and A jump, and JMP. Dash jump means relative address means and if the address locations are 250 bytes of address locations, then we use dash jump. If it is up to 11 bits or 2K bytes, 11 bits means 2 power 10 is 1 kilobyte. 2 power 1 is 2. So 2 into 2 power 10 is 2k. So 2k means 11 bits. So if address is specified by 2k bytes of data address locations, then use age. If it is more than 2k up to 64k, then we use LGEN. And indirect jump, we can also jump to the address location using JMP. So then we have tried JMP at the rate of A plus DPTR. And these are all conditional jump instruction JC. Jump to relative address if there is a carry. J and C. Jump to relative address if there is no carry. What is relative address here? Right. DJNZ comma here. What is here? Here is written here. Decrement and jump are no zero. What we are decrementing? We are decrementing the R3 value. What is R3 value? Here R3 value is initialized by 255. Decrement R3 value, then it becomes 254. And here, if there is no jump or no zero, if there is a zero, keep the buzzer for a while and then goes to this location. Dash jump here. Right. If there is a zero, then execute clear P1.3 and return interrupt. If there is no zero, jump to this place. If there is a zero, execute these two instructions. Understand? So that is the branching and jump instructions. Otherwise, main, L jump, main. Right. Where it is going, LGN main, where main is written here. Between this instruction, we are having in between so many instructions. This is what we call the LGNs and agents. So, but this jump instruction will go for main instruction without checking any condition. But here it is a conditional jump. Increment jump on no zero. So here you can see that J and Z is stands for jump on zero or jump on no zero. Right. So here this especially this conditional jump instructions are seeing the status of program status word. Okay. And all the conditional jump instructions are some short jumps. Rotate and swap instructions. And rotate and swap instructions are used to rotate and they swap the data from one point to another, left side to right side to left side. So that's why here we are having rotate left and rotate right. So RLA stands for the content of accumulator is rotate to left side by 1 bit position towards left side. Rotate left with carry means we are having carry also of additional programming as a function programming. Along with that carry, we have to rotate the content of the how we will see here. Suppose I am having R and A. This side is called left side and this is called as right side. Now we are moving the content of this. This is the accumulator 8-bit positions. Now it is moved into left side, and this bit will be shifted to this side. So that is what we call the rotate left operation. And rotate right with carry. So this is the carry position, and this is the accumulator position. So after adding the carry, ESW store this carry position. Now what is happening? Rotate right side it is copied. Right, this bit value is copied into carry, and the carry bit is copied into this bit position, which is rotated towards right side. Yes, that is we have to call it rotate right operation. And here we are having the different rotate operations. Rotate left with carry, rotate left with sorry, rotate left of the accumulator, rotate left with carry, rotate right with of the accumulator, rotate right with carry, and this is the swap instruction. The swap instruction executes swap A means the content of accumulator itself will be swapped or rotated. But this is not a bit oriented. This is a nibble operation. Means lower nibble copied into higher nibble and higher nibble copied into lower nibble. Right. What is nibble? We know that 4-bit combination is called as nibble, 2-bit combination is called as double bit, and 8-bit combination is called as byte, and 16-bit combination is called as word or 2-byte representation. So here nibble to nibble. See here, swapping the lower nibble and the higher nibble of the bits of accumulator is called as swap A instruction. So this lower level confidence to higher level and higher level confidence to lower level. So this swap instruction mainly used in computer networking programming execution. So here I want to execute number 64 addition example. So I want here x equal to 1 to 7h and y equal to 1 to 7h. So how the addition takes place? Addition takes place. So 8 will be added with 3, 7 will be added with 7, and 2 will be added with 3, and 1 will be added with this 1. So that's why here 1 to 7 8h hexa. This is hexadecimal number. Each number is 4-bit representation. So here I am having 4 hexadecimal number. So 4 into 4 equal to 16. That's why this becomes 16-bit addition. Right. So same operation, new R0 comma 78. So 78 is goes to R0 memory location, and 7A is added with A, and add A comma R0. And now we are sending this data A to DPL because this DPL is the lower band of DPTR. Move R0 comma hash 12. 12 is the data value of the X value, and 13 is the data value of Y value, which are higher bytes, and these two are added again because in previous addition. Here this may generate any carry. That carry is called as auxiliary carry. In that case, we have taken that carry, right? Then we have tried to add with that auxiliary carry, and then A comma R0, right? So what is R0? 1? What is A? 1? Now we are adding the result with A comma R0. Now move DPH comma A means the content of A is moved into DPH registers. What is DPH? DPH is nothing but DPTR. DPTR stands for data pointer. It has lower byte and higher byte. This is called DPL is lower byte and DPH is higher byte. So after operation of the addition, we are sending the 16-bit value into DPTR register. So thank you for your kind cooperation. If you have any doubt, please ask me.